Hello, good morning. I want to talk to you about some work I'm doing with my co-PI DK Panda and the MVAPICH team at Ohio State University. It's a little bit different from the talks we've seen so far that are we also need to study the communication that's the focus here, is looking at how some of the communications among the processes run at really large scale, what things are going well, and study. The drivers here is that as our systems evolve, we now have multi-core processors are in all of our systems. Interconnects are involving having more features, RDMA support and support for collectives, hardware support for collectives, and we'll see a case where that's actually working quite well on Blue Waters. And we have accelerators, and I show a bunch of machines here. Some of these machines have accelerators on every node. Blue Waters is a nice have a out accelerators and the XE6 nodes without accelerators, 7 nodes with NVIDIA GPUs. And that's actually a model that reflects the ecosystem below it much better, that many campus, our regional center, we have some nodes with accelerators and some without, and that's by both cost and also a feeling that there are codes that do well on the accelerators and other codes that maybe don't need the accelerators. So these mixed systems are actually quite prevalent at the next tier. As we try to ready our infrastructure and our middleware software, we need to understand and deal with these complexities. So if we look at communication on a supercomputer now, it's actually a pretty complex features advantage of that the hardware designers have provided for us. We have shared memory within a node, but as we have multiple sockets and our chips within the sockets themselves get more and more complicated, that is a NUMA, non-uniform memory access shared memory. So when we're transferring between sockets, node, being aware of that, times for communicating there. And then our accelerators are currently connected via an I/O bus, and where those accelerators are connected, which socket that I/O bus is connected to, at different bandwidth characteristics for all these scenarios. And so when we build our communication library, understanding that. And we expect this, you can't build a really, really large system without some hierarchy in this. So we expect that kind of complexity is not going to go away. Other thing we have is right now these libraries are being developed in the lab. We have maybe 1,000 core processor. And the team works on actually a range of systems. We work on lab system, the Ohio supercomputer system, and with this project on Blue Waters, so that we can understand the communications. MVAPICH is an MPI library. Historically, we realize that there are other programming models. Some people don't like MPI for programming. Out here don't like the detail you have to specify in an MPI program. PGAS models are an alternative that has that higher level interface. And all these models map to a particular view of what a parallel machine might look like. So a shared memory model access a single global memory. The PGAS models, from a programming point of view, sort of the same model, but supported across distributed memory. So a view that we have one global memory, but implemented on distributed memory. Processes. Our many core accelerators have their own programming models. Trying to run and take advantage of, often have to bridge across different parallel programming models. Looked at a few questions during our Great Lakes Pep-scale computing. First, so before we could work with applications, we've focused on some fundamental things, understanding where things are now on the system. Because when you go to running on hundreds of processes, suddenly communications that are short when we're running on hundreds or even 1,000 have a big impact on application performance. So understanding as communication, and then that tries to take advantage of all the nodes in the system to quantify performance. So we didn't run it on Waters, but we looked at how do you utilize both the XE6 and the XK7 nodes. I think probably know about MPI if you're running at the scale of Blue Waters. And we want to look at, we didn't run on 1 million processes here, but we have run up to processes on this system to look at the performance. Scaling well, where in scaling to really large number of cores do you start to see that maybe the algorithms which are designed on having challenges. Studied collective performance. In particular, we looked at broadcast, reduce, and gather, and where aspects of the underlying interconnect are helping us challenges. It's hard to provide an interconnect with infinite bandwidth and zero latency. That's not. Look at that here. And we looked at broadcast. We have lots of charts here, and I'll probably have typically all these charts have latency, so the time taken for the communication operation, y-axis, message size on the x-axis, and then number of processes in the different 12 processes. Actually run a range of places, and so we can see that have some places where we have some jumps that we processes that when we go from 6, we start taking more time, and this is likely an issue of topology. The number of nodes for 128 processes is 4 nodes. With a torus, those can all be next to each other. We can have high bandwidth. Larger number of processes. Variability at the larger number of processes. Because the particular architecture factori are easy to scale to very large numbers, but they have bandwidth limitations. So our broadcast, which is fairly dense, size, we can see challenges. And we actually saw a very interesting, when we get to really 16K to 128 processes, saw on the 128K processes this spike, which was actually repeatable on several jobs. And so this is MPI, so we don't know the underlying algorithms. So all MPI libraries for collectives have a bunch of algorithms to choose from, and they'll choose based on message size, system size, and and then again, we see numbers of processes, more variability in the time, which you would expect, possibly more contention with other processes. Spread across more of the machine, so bandwidth impacts. Shining star on the Blue Waters system. Network has support, hardware support for the reduce. So small message reduce is very common in scientific codes, particularly iterative codes used for got an iterative code, and you want to run it at really large scale, Blue Waters is an excellent. See a little bit of an upturn in the latency at the byte. So the hardware support is going to have some fixed size buffers and things internally. So probably hit some underlying parameters. And as we go to larger scales, even at our highest scales, we don't really start seeing some increase in latency till we got up to the 128K. Show that a little bit here. We just normalized the latency of our largest run on 128K processes to our smaller run. The broadcast does have some scaling issues, but reduce except for the few. Allgather, we just have a, Allgather is a dense collective. We move a lot of data. All the processes back to a root process we specify. And because of that, it sort of has a hotspot behavior, lots of data coming to one place. Run into, as we get with large message sizes with Allgather, some. Looking at the MPI performance, extensive operation is very good. Some congestion at the very large process size, number of process counts. And for dense collectives, Allgather, all-to-all is one commonly used in FFT. Similar issues than looking at alternative ways to do that exchange. If you collective operation on a subset of processes, make it smaller. On blocking variants in MPI3 so that you could do collective to return, or algorithms will come. So if we go on to PGAS models, communication underneath, a little bit easier programming interface, API. Easier to express irregular communication in PGAS models. So we looked at two such models, parallel C. Operations and collective operations. So we have both one-sided point-to-point operations in I 2 and 3 RMA. Set of collectives, not as rich of a set as models we looked at here. Get a good latency. We are having higher costs for put. So one-sided messages, the process requesting it initiates that, does not require process on the other end to be aware of it. However, for the process that initiates it to know it completes, if it's doing a get of data, when the data arrives, it knows. It knows. If a process is doing a put of data to another process, it needs to have additional synchronization. So that is a little get some. I'm going to not get to. I'm going to jump to my summary slide because I'm down to a minute. And well, I'll go real quick. We also looked at HPL. This work was originally done on OSC system. It was presented in cluster last year, so we wanted to see how that would take that same approach and run it on Blue Waters. So after working with the team here to allow us to running HPL just on GPU nodes, just on the x87 nodes. Then we ran it just on CPU nodes. And then we looked at our hybrid case. So in the hybrid case, we're not running on, not launching matrix sizes that are ideal for either, because we need to fit multiple MPI processors, balance the compute power there and not have them waiting on the CPU nodes. But we do get a gain in performance. That is, our overall performance with using GPUs better than if we just ran fully on CPU. So that is, there is some, you can get work out of the full system. You can get some additional, and it's one that we actually rarely see this reported in runs because of the challenge in working across good performance out of both resources. That's what this work was about. I will skip the summary and go to